Welcome to homework.
Now, manufacture of hydrogen is carried out using a process known as steam reforming process, in which methane is reacted with high pressure steam to form carbon monoxide and hydrogen. This is the first step of the reaction, and this is an endothermic process. Endothermic. And in the second step, in the secondary process, again the same methane is partially oxidized with oxygen to form carbon monoxide and hydrogen. You can see, if you look at the molar ratio, there is there are 2 moles of reactants. Reactants are 2 moles, while products are 4 moles here on the first step, and here it is reactants 1.5 mole, and here it is 3 mole. So there is an increase in number of moles, and also the second reaction is also endothermic with delta H equals 26, approximately 26 kilocalories, 36 kilocalories per mole. It is 36 kilocalories per mole, or kilojoules per mole. Okay. Now we have to find out what is the effect of temperature and pressure on this reaction. Now, temperature, this is an endothermic reaction. Endothermic reaction means heat is reactant. Heat is considered as a reactant. So if you increase the amount of reactant, the reaction will favor in the forward direction. So the product is favored at a high temperature for both the processes. Now, there is an increase in the number of moles from reactants to products, as we have shown here. 2 moles of the reactant in the first step, 4 moles in the second, on the products. Again, the second step, 1.5 moles is increasing to 3 moles. Now, what happens here is, when the pressure is reduced, when the pressure of the system is reduced pressure, it will drive towards an increase in the pressure, which is equivalent to increase in number of moles. So the reaction will be diverted in the forward direction at reduced pressure. But in practice, the reaction is carried out at high pressure. That is because hydrogen is directly consumed in the process for the manufacture of ammonia. And ammonia manufacture is a high pressure process. So since this is instantly used, in practice they are using high pressure, even though the equilibrium is favored to a reduced pressure in the reaction. Now let us look at the second part of the question. Now, for the second part of the question, in the second part, we have to find out what is Kp of the reaction. Now, Kp equals Kc into RT power delta N. Now, for the first step, delta N, for the first step, number of moles, difference in number of moles, delta N equals 4 minus 2. So we can write Kp equals 18, Kc is given, Kc equals 18 into 0.0821 into 1073. This is the temperature of the reaction in Kelvin whole square. So that is equal to, if you calculate this, you will get a value 1.4 into 10 power 5. So this is the Kp of the reaction. Now, thirdly, we have to find out the equilibrium concentration. To find the equilibrium concentration of reactants and products. Concentration of reactants and products at equilibrium under the given condition. The initial concentration of methane at initial concentration of 15 atmosphere. Now, let us, to do that, we'll generate an ICE table for the process where we write the initial concentration of all the components, then change in concentration, change, and equilibrium concentration. Equilibrium concentration. Or in atmosphere, first we are giving the value in partial pressure rather than concentration, because so all in atmosphere. Now first the reaction is CH4 plus H2O giving CO plus 3H2. The initial concentration of methane and steam is at initial pressure is 15 atmosphere each, and starting point this is 0, and here it is minus x. If x is a number of moles being converted, minus x, and this will produce 1 plus x, and for each mole there is a formation of plus 3x of hydrogen. Now, let's look at the equilibrium concentration. It is 15 minus x. This is the amount of moles of methane that is left. Steam also 15 minus x. And here it is x and 3x. Now, from these values, we have to find out the value of x from the equilibrium constant Kp of the reaction equals partial pressure of carbon monoxide into partial pressure of hydrogen H2 whole cube divided by partial pressure of methane into partial pressure of steam H2O. Now, substituting these values, we will get this equals x into 3x whole cube whole divided by 15 minus x into 15 minus x, 15 minus x whole square, which is equal to 27 into x power 4, 27 x power 4 divided by 15 minus x whole square, and this value is equal to Kp, which we have already found out. It is 1.4 into 10 power 5. 10 power 5. Now we can make the calculation simpler. This can be This we can express. So we can simplify this equation by taking the square root on both the sides. We will get this is 3.7 into 10 square equals 5.2 x square divided by 15 minus x. Now this can be written as 5.2 x square plus 3.7 into 10 square x minus 5.6 into 10 cube equal to 0. Equals 0. So to put the bracket here. Now when we solve this quadratic equation, we will get two values for x. X equals 13 atmosphere and the second value is negative, which we will not consider. It doesn't have a meaning. So at equilibrium, the equilibrium concentration, at equilibrium, we will have partial pressure of methane equals 15 minus 13, 15 minus x. 15 minus x equals 15 minus 13 equals 2 atmosphere. This is the contribution from methane at equilibrium. And partial pressure of steam, again a reactant, that is also the same value. We can just write the same thing here, equals 2 atmosphere. Partial pressure of carbon monoxide equals 13 atmosphere. And you can see the contribution of hydrogen. Partial pressure of hydrogen equals 3 into 13, that is 39 atmosphere.